Thank you very much for inviting me to present this work here. Somewhat unusual setting, so I hope my talk is going to be well understood. So let's see. Okay, that works. So my talk is going to be about rough solutions of nonlinear wave equations. Specifically, I want to focus on a special type of geometric wave equation where such rough solutions up until this point were not known to exist. But because it's a somewhat technical subject and maybe a little delicate for people who don't work in this, I want to give a bit of a general introduction to begin with, explain a bit the intuition, and sort of try to avoid aspects which are maybe overly technical, or relegate these to the very end of the talk. So very generally speaking, so I'm interested in kind of semi-linear wave equations, although the hope would be that the techniques that are being developed in this setting may also apply to quasi-linear wave equations. So for now, let's just look at a sort of simple-minded general model. Box U's function of U and del TXU, the first derivatives of U, which we consider on a Euclidean space, Minkowski space, excuse me, of them spatial dimension D. So of course, there's the general issue of local well-posedness in HS spaces and Sobolev spaces. These are the natural spaces to work with nonlinear wave equations. So very generally speaking, you propose initial data, which is a pair of functions in HS and HS minus one, and you're trying to construct solutions which live in that space, depend continuously on time with respect to that topology. You also need to have some sort of LP integrability to make sure that, let's say, if the nonlinearity only depends on U, otherwise you also need some kind of LP integrability for the derivatives to make sure that your solution makes sense as a distributional solution of your problem. And the question that arises is, how small can one choose S? Now, this is not just an academic question. There are some very good reasons for this. On the one hand, for some equations, there's really not very much a priori control that you have on solutions. You may have a controlled energy, and if you want to sort of control the global evolution of large data solutions, then you basically have to work at the level of regularity of that conserved quantity. And so that's a very strong impetus, has been a very strong impetus to kind of push the requirements for local well-posedness to that level of a conserved quantity. That's particularly important for energy critical equations that I will talk about soon. Another even more radical attempt is to kind of try to understand solutions in terms of a Gibbs measure, which one can construct for some of these models. And so typically the functions in the support of a Gibbs measure are very rough. And so people are trying to evolve data in the support of this Gibbs measure and then get a global result by means of preservation of the Gibbs measure. And more recently also, it has emerged that some of the techniques that people use to construct these rough solutions, they seem to be casting new light also on classical solutions. So here the idea of randomization is very important. And the fact that apparently generic features of these equations are oftentimes much more benign than certain pathological extreme features in certain situations. And randomization may not only be able to allow us to construct very rough solutions, but it may also, for example, help to show better bounds for generic solutions, or get better qualitative behavior for even classical solutions. For example, there's very interesting recent work to Burg and Thomann on MLS, which uses this idea to kind of get better generic behavior of solutions of an equation where this classically could not be done. Okay, so how does one lower S? So of course there are certain basic steps one can take. First of all, if you start with a very simple-minded equation, this pure power nonlinear wave equation here, for example, the first thing you can try is use the energy inequality to do a fixed point argument. And you see if you work in HS, that forces us to control the HS minus one norm of the nonlinearity. And this you can do by fractional Leibniz rule. For example, let's say S is larger or equal than one. You put one factor into HS minus one, and the rest you bound in the L infinity norm. Here you do not take advantage at all of the integration. The integration in time should somehow help you because it's kind of the opposite of differentiation. However, with this naive ansatz, you don't even take advantage of this. And of course, this costs a lot of derivatives. So bounding the L infinity norm of U costs more than d over 2 derivatives. And so this is kind of what you can get with this approach. But then at the end of the 80s, people realized that there's these Strichartz estimates, which take into account certain quantitative features of solutions of the free wave equation, namely the fact that they have this dispersive decay. And this allows us to actually bound certain LTP, LXQ mixed norms. There are certain technical constraints on these PQ exponents. They have to be Strichartz admissible. This is the condition that 1 over P plus D minus 1 over 2Q is less than or equal than D minus 1 over 4. In particular, if you have equality here, one would call this a sharp Strichartz admissible pair. And then there is, of course, the scaling compatibility here. Again, this shows that if you put P and Q equal infinity, then you get exactly S equal D over 2 here. But if you put P less than infinity, then you will have to use somewhat fewer, you can lower S. And so you use somewhat less regularity to control these norms, which is what you want if you want to improve the local well-posedness. And so, okay, so this is maybe a little technical, but still kind of gives you a kind of nice idea. So, so how can we exploit these Strichartz estimates to improve the local well-posedness for this kind of simple-minded equation? Well, if you take a product of P of these factors U, and you assume that they are supported at frequency N1 up to NP, which are ordered, frequency refers to the Fourier variable. Then again, you can do this by using Verhulder's inequality and fractional Leibniz, but this time you take advantage of the time integration here, and you put P minus 1 of these factors into LTP minus 1 Lx infinity, and you exploit the Strichartz estimate. And if you do this carefully, you see that if you require this SC, this critical Sobolev exponent, many derivatives require this much regularity, then everything balances out at the end of the day. You can sum over all of these frequencies and there's no loss involved. So from at least, I mean, you have to make certain assumptions here on P and S and so on, but let me not worry too much about this. So this shows that just using these Strichartz estimates under certain restrictions suggests that there is sort of a natural optimal kind of regularity, this S sub C regularity, which you need to get good local well-posedness theory. And this SC has a nice interpretation because it is exactly the Sobolev exponent such that the corresponding H dot homogeneous Sobolev space is left invariant under the natural scaling associated with this kind of equation. So somehow this, just from these considerations on Strichartz estimates, this gives you kind of a natural lower bound on how much regularity you should have to require to get a good theory. And it turns out that if one puts certain technical restrictions, P shouldn't be too small. For example, when you're in 3 space dimensions, then P has to be at least equal to 3. Then it turns out that this SC is indeed sharp in the sense that things go bad if you put initial data in a space of lesser regularity than this. And this, there are actually rigorous results on this from the early 2000s. So Gilles Lebeau and Chris Colliander-Tau constructed counterexamples that show that you need this much regularity by constructing certain highly oscillatory solutions for these equations. However, I mean, the question arose, people asked the question, well, how representative are these counterexamples? Maybe this is not, in some sense, not a generic feature. And so in '96 already, Jean Bourgain introduced one of the key, very important ideas for this talk. So he encountered a kind of similar situation when he was studying the cubic NLS on the 2-dimensional torus. And he was trying to evolve data, generic data, in the support of the Gibbs measure for that problem. And it turned out that those data formally didn't have enough regularity to kind of get a good local well-posedness theory. And so the remedy that he used was he randomized on the data, and he showed that almost surely he could make sense of the evolutions of his data, although, like, classically speaking, they were not regular enough. And this concept was then much further pushed also in the context of the nonlinear wave equation. on compact domains. All of this was in compact domains for a reason that I will explain. In particular by Burg-Tzvetkov. There was also work by Tadahiro on the KDV equation. And so let me expand a little on this. So what is the key ingredient that goes into these results is a basic fact from probability theory, which is this Khinchin's inequality, something very basic. So assume that you have a sequence of coefficients Cn, and you look at linear combinations of these coefficients where you multiply them with these independent real mean zero sub-Gaussian random variables, and then you average over the random variable. And then you get this interesting inequality, which says you can bound this in terms of the square sum over these coefficients with a certain weight depending on the LP norm that you're using. So this beats somehow the very naive inequality that you get if you just L1 sum over these inequalities. And in particular, you get this kind of estimate on exceptional events. So the likelihood that this weighted sum is larger than lambda becomes extremely small. If lambda is large, it decreases super exponentially in lambda. And this is something which is very useful in the context of these wave equation examples, as we'll see, because the coefficients Cn, they will basically be L2 norms of frequency localized pieces of our solutions. And because you have the orthogonality of these pieces, you control the square sums over these L2 norms of these frequency localized pieces. You do not control the L1 sum. And so Khinchin's inequality becomes very useful in this context. So the point is you replace L1 sum by L2 summation here. All right, so how is this useful, let's say, in the context of what Burg and Tzvetkov were doing? Let me just very briefly outline what they were doing because it introduces some interesting things. So let's say M is a compact, smooth manifold. You look at the Laplace operator on it. You have an orthonormal set of eigenfunctions corresponding to eigenvalues lambda n squared and count of a family. And then you can one can derive these SOG estimates, which bound certain LP norms of these eigenfunctions in terms of the eigenvalues. These are optimal in general. One can improve them by averaging certain symmetric situations, but in general, they're optimal. So for example, in 3 dimensions, you have this inequality for the L4 norm of these eigenfunctions. And what Burg and Tzvetkov then do is they look at the wave equation on such a 3D manifold, and they randomize the initial data by representing them in terms of this basis, orthonormal basis of eigenfunctions, and weighting them with Gaussian variables. And what you see is that because of combining Khinchin's inequality with this SOG estimates, there's nothing more. You just put these two things together here. You see that if you look at the L4 norm of the free wave evolution, let's say on a local time interval, then you have to pay 1/4 derivative as opposed to 1/2 derivative. Again, this is in 3 dimensions, so this is the right scaling. So 1/2 derivative is what you have to pay classically, and in the random sense, you only have to pay 1/4 derivative to bound these expressions, bound the L4 norm of the free wave evolution of these randomized data. Now, okay, so this is just for the free wave evolution. So how does one apply this then in the context of the nonlinear problem? Well, so here there's a very important idea, it's kind of simple, but it's extremely influential. And nowadays this goes by the Bourgain-Dapprato-Debuche trick. Bourgain kind of introduced this first in the dispersive context, and Dapprato-Debuche in the parabolic context. So to construct, let's say, a solution of the cubic wave equation on such a manifold with randomized data, you look for a solution which can be decomposed into the free part, the free evolution of the randomized data, plus a correction term, W. And the correction term W will have to solve this inhomogeneous wave equation. It's driven by the error that's generated by the free approximation here. But you have trivial data for this. And so now if you look at the Duhamel propagator applied to this source term here, which is U omega plus W cubed, then right away you see that there's a smoothing effect that this Duhamel propagator has. This is one of the nice features of the wave evolution. And this smoothing effect allows you to run a fixed point argument for this correction term W in a space which is smoother than the u sub omega, u omega, the randomized random part. So there's this decomposition into a rough random part plus a part w, which is smoother than the rough part. Okay. Now, okay, so this method works on compact manifolds because for this randomization, you need a countable family of these eigenfunctions used in the representation. And what's also very important, of course, to get the smoothing effect here that I was referring to, you want to make sure that there are no derivatives in the nonlinearity, of course, because as soon as there's a, a derivative in the nonlinearity, this smoothing effect gets destroyed. And we will soon see exactly how this happens. So the question then arises, well, first of all, how can one sort of implement something like this in the Minkowski space? And also, how can one deal with more complex nonlinearities, equations which are maybe more physically relevant? There's this large collection of geometric wave equations, and we will look at a specific example here, which have some kind of physical significance, but they typically involve derivatives in the nonlinearity. How can one find an analog of this kind of procedure in this kind of more complicated setting? Now, one way to kind of transpose things to the Minkowski setting, which this was an early attempt, was to use the Penrose transform to compactify it. One can prove result of Burg-Tzvetkov type in this way, but sort of a simpler approach, which is also very nice for me to explain here. This was originally introduced by Jonas Luhrmann and Dana Mendelssohn in 2014, and so there the idea is so very natural. So you look at representations of your function on an RD in terms of the Fourier transform, and then you what you do is if f hat is the Fourier transform of your data, your function in RD, which let's say is an L2 function, you partition RD into cubes of side length 1, and then each one of these cubes, which is now a countable collection of cubes, you hit with this random weight function LC of omega, and that is your way of randomizing the data in this setting. And immediately you get some very powerful improvements that way. For example, let's say we want to bound the LP norm of such a function, which typically requires using the Sobolev inequality, right, going from L2 to LP. And if your function is at high frequency, then you have to, of course, pay a certain power of the frequency to do so. However, for these randomized functions, you basically have to pay nothing. And the reason for that is if you apply Khinchin's inequality here, let's say with LQ weight with respect to the random variable, Q has to be larger or equal than P for this to work. You see by Khinchin's inequality, this gets reduced to bounding the square sum over these cubes of the cube localized pieces of F. So what I mean by this is that you take F, you take its Fourier transform, and you localize the Fourier transform to a cube, and then you undo the Fourier transform. That was what PCF means. So you can bound this averaged LP norm in terms of the square sum over these localized, the LP norms of these localized pieces of F, up to a certain weight square root Q, which you have to pay because of Khinchin's inequality. And now to bound the LP norms of these localized pieces, you do use the Sobolev inequality, but basically these pieces are like frequency 1 functions. I mean, if you just multiply them with a suitable phase function, there will be frequency 1 functions. And so therefore you pay nothing, you just pay 1 to apply Sobolev inequality here. And you can bound this in terms of square root Q times just the L2 norm of F without having to pay any penalty in terms of the frequency that the function moves at. And in particular, this means that if you look at almost surely at the event that the LP norm of this randomized function is large, it becomes extremely small. It decreases super exponentially in lambda. Okay, so how would this be useful now to implement, let's say, for a simple-minded wave equation here? I've written down the energy critical wave equation in 3 + 1 dimensional Minkowski space. Well, I mean, here it's known, this is a very old story, that one can solve this for data of energy of H1 regularity by working with the LT5 LX10 Strichartz estimate, which is available in 3 dimensions. And it's not sharp, it's a non-sharp Strichartz norm. And so now I can exploit this randomization of Luhmann and Mendelssohn. I can pass to a sharp Strichartz norm, which is, for example, LT5 LX10 thirds, which I can bound in terms of the H2/5 norm of the initial data. And then I can now randomize things. And okay, so when I randomize here and I again work with the LT5 LX10 norm, by Kinchin, I reduce to the square sum of the LT5 LX10 norms of the frequency localized pieces to cubes in a Fourier space. And then each one of these frequency localized pieces to cubes in Fourier space, I can again bound in terms of this trivial Sobolev inequality in terms of the LT5 LX10 thirds norm. And for this, I just have to pay H2/5, the H2/5 norm of my initial data. So I've gained 3/5 derivatives for this procedure. Using this and the Burg-Tzvetkov trick, you can then almost surely solve this kind of wave equation in a much less regular space for H2/5 space, let's say, for small initial data. All right. So in fact, one can improve this more. So this is maybe a somewhat technical remark. Of course, this argument is very crude. So I'm just using this simple Kinchin's inequality and its manifestation for the Sobolev inequality here. And I just use these Strichartz estimates as a black box. But it turns out that this square sum here that you have in the here in the middle of the page over the LT5 LX10 third norms over these cube localized pieces, you can actually gain even more for these things. And that's due to these Klainerman-Tataru type improved Strichartz estimates. Let me just very briefly say, so these estimates, they result from the observation that Strichartz estimates, they result from interpolating between the dispersive L-infinity bound and energy conservation. And it turns out that if you have a free wave, which is actually localized in Fourier space to a small cube, then you can improve the dispersive decay. You get an extra factor mu, which measures the width of this cube, let's say. If your function is, let's say, at frequency 1 and your width is 1/1,000th, then you gain a factor of 1/1,000,000th for this dispersive decay. And by then proceeding with the usual TT star argument, one can improve for these square sum type Strichartz type norms, one gets extra gains. And using this, one could even improve slightly more the preceding example. All right. So by the way, so for the sequel, so these kind of square sum Strichartz norms, which beat scaling, somehow I will refer to these as redeeming bounds somehow. They're bounds that are better than what scaling considerations would suggest. Now, all right, so let's move now towards geometric equations. What happens if derivatives are present in the nonlinearity? So here's a very simple model equation, this box U del U squared. It's an equation which really doesn't have much of any structure. It's just, it has these derivatives there. And if you try to run this Burg-Tzvetkov ansatz, it fails, like I said, because for the Duhamel integral, you're not going to gain smoothness. And more specifically, so one can analyze this more closely, the main issue comes from low-high interactions in the nonlinearity. When you have two high interactions of comparable frequency, then you can still gain something. But if you have this wide discrepancy between the two frequencies, then there's nothing you can gain, basically because this inverse square root of the Laplacian gets killed by the del that hits the high frequency term, and there's nothing left to gain. And so the question is, well, I mean, for equations of this type, can one do anything? Now, okay, so what you see is there is this specific problem that comes up here, which is this low-high interaction term. And this has a long story, these kind of expressions. It came up first in the work of Bonilla, who called it the paraproduct. So it's this kind of imbalanced product of a low frequency term and a high frequency term, and Boni's incarnation, you sum over all the frequencies. But this has come up time and again in the theory of particular geometric wave equations. For example, the theory of wave maps, Maxwell-Klein-Gordon equation, Yang-Mills equations. Terry Tao's work on these the optimal small data global existence for wave maps, for example, this played a major role. Sometimes you can get rid of these bad paraproducts by using gauge invariance and gauging these things away. But sometimes, such as for the Maxwell-Klein-Gordon equation, which I will talk about more later, and the Yang-Mills equations, you cannot get rid of them. They're just there, and they cause fundamental analytic difficulties. This issue also came up in the large data theory for these problems, again, the energy critical wave maps, Maxwell-Klein-Gordon, via concentration compactness approach. We'll talk a little bit more about this later on. And it forces a variant which I call the covariant concentration compactness method. These paraproducts play an important role in paracontrol calculus by Gubinelli and Keller-Perkowski. They come up in Björn Bringmann's work, which I will talk about in a minute a bit, concerning this special wave equation model that I just mentioned. Comes up in the theory of random tensors by Deng Nach-Modue, and also play a key role in this result that I will discuss later on about supercritical global well-posedness of a certain geometric wave equation and the Maxwell-Klein-Gordon equation. Now, okay, let's go back to this this wave equation here, box U del U squared. There have been recent works, very interesting works, related to the local well-posedness to this problem. And with the question, can we beat the status quo? Can we go below what classical theory would tell us is the minimum regularity that you need to construct local solutions of this? And people have done this in different dimensions. So in 2 dimensions, there was a recent work due to Chanilo, Jubak, Mendelssohn, Nafmod, Stafilani. Classically, you should require at least 7/4 derivatives in H7/4 plus to make sense of local solutions. But what these authors show is that by randomizing the data and looking at sort of the iterative scheme that you do to solve this problem, you can actually ensure that all the iterates are bounded in H1. So you can go much below this H7/4 space, and still get a priori control. But the problem was, like, you cannot show that this actually converges, this kind of procedure. Similarly, in 3 dimensions, there has been a recent work to do Björn Bringmann. In 3 dimensions, this model should require H2 plus regularity to actually get strong local well-posedness. And what Bringmann shows is that by randomizing, he can actually strictly go below this, not very much, but he can strictly go below H2 regularity and construct actually local solutions. So in his case, the iterative scheme actually does converge. Now, so what are key ingredients of this result of Bringmann? So there is this paraproduct which we cannot treat in a perturbative fashion. So there is an important innovation, which is that Bringmann, he kind of breaks this paraproduct into what I would call a strongly imbalanced paraproduct part, a part where the lower frequency is at most n to the gamma, where gamma is some number strictly less than 1, while the upper frequency is n. And then you have an error, and the error it's still of paraproduct type, but it's not so bad that you cannot treat it perturbatively. So the error here, which I've moved to the right-hand side here, can be treated perturbatively. And what he then does is he shows that, well, by interpreting the equation on the left as an equation and localize the frequency n as a wave equation for the frequency n piece of u, which is now some kind of, it's no longer a free wave equation, but it's now some kind of magnetic potential type wave equation. Then we can show that by randomizing on the data, we can actually improve, we can show redeeming bounds for the frequency n piece of u. And you can then implement a kind of Bulgar-Debye-Stapato type decomposition of that piece. But the construction of this piece is much more sophisticated. The rough part is not a solution of the free wave equation, but it is interpreted as a solution of this coupled, this magnetic potential type wave operator here. And of course, you see one difficulty that arises when you do this. The free wave equation has the property that the Fourier support of the solution is preserved under the flow. However, if you look at this kind of strange wave operator that I've written down here, then the Fourier support gets smeared out. And so that's in particular why it's very important to localize the frequency of this magnetic potential term del U here to size at most n to the gamma in order to ensure that the solution of this equation still inherits some kind of randomization and redeeming bounds Otherwise, we would lose these completely. So there's some kind of delicate trade-off between the gains that you get through randomization, the redeeming bounds that you obtain, and on the other hand, the smoothing effect that you obtain for the error and that you move to the right-hand side. Now, the method that he obtains these redeeming bounds for solutions of this strange wave equation here, it's different than what I will talk about later. So basically, it's everything here is local in time, and at some point one uses a Gronwall estimate. So one kind of uses energy methods to do this. And this kind of method is certainly not very well suited to obtaining global solutions, right? Where you have to retain some kind of dispersive behavior of solution. So this method is not so well suited for this. But on the other hand, of course, the equation that Brinkmann looks at has basically very little structure, and you wouldn't even expect to get good theory for global solutions to begin with for this kind of problem. So I mean, it's well known that from work by Fritz John in the 80s that for an equation of this structure, box U is del U squared, basically any kind of solution, even with very small but non-vanishing data, will blow up in finite time in 3 dimensions. And so this is kind of it's not a very good equation to study beyond this local well-posedness issue. It's not a Hamiltonian equation, so you certainly couldn't dream to construct a Gibbs measure for it. However, recent years have shown that there is a very natural class of equations, which I've already mentioned, some examples, wave maps, Yang-Mills, Maxwell-Klein-Gordon, which shares certain features with this simple model here. There are derivatives that come up in the nonlinearity, but which have an amazingly rich structure. So there's a very rich geometric structure, very rich analytical structure. And so for these kind of equations, you can hope to expect much stronger results. And so in particular, the question is, can one construct rough solutions for these equations, and particularly globally in time? All right, so then now I have to specialize to one of these geometric wave equations. The reason why is not that this equation is particularly important, but it's that it is somewhat simpler than some of the other geometric wave equations, such as wave maps, Yang-Mills equations, or actually fully quasi-linear equations. And there is a very well-developed theory by now that we could build on. And so we could avoid some technical problems by having to rebuild the theory from scratch. So the Maxwell-Klein-Gordon system, it describes the interaction of a massless particle field, which is modeled by a complex valued function phi of t and x in Minkowski space. Later on, I will just look at one specific case, namely when you're in 4-dimensional 4 plus 1 dimensional Minkowski space. But for now, I just mentioned this in general, the model. There's also an electromagnetic field, which is modeled by this vector valued potential function here, A sub alpha, which takes real values. And then Maxwell-Klein-Gordon system corresponds to critical points of a Lagrangian action density functional, which is given by this expression here. So D sub alpha refers to a covariant derivative operator, D alpha plus I times A alpha. And F alpha beta corresponds to the corresponding curvature form. Now, it's an abelian gauge theory. And so in particular, the curvature is very easy to express. There is not a commutator term here, which you would get for the Yang-Mills equation. And then if one writes down the Euler-Lagrange equations of the system, then you get a coupled system of equations. For the particle field, you immediately see that this is some kind of wave equation. It's really a nonlinear wave equation. It looks linear, but it's nonlinear because there are these terms that couple phi with A. And on the left-hand side, it's not so clear that it's a wave equation. It's some kind of complicated system of equations. However, the character becomes clear once one exploits gauge symmetry. This means that there is a natural group of transformations acting on the space of solutions of the system. And in particular, one can fix the gauge. And for my talk, I will always work in the Coulomb gauge, which means that the spatial gradient of the electromagnetic potential here is set to 0. And with respect to this gauge, you see that your system becomes a combination of a wave equation for phi. There's a system of wave equations for the spatial components of the electromagnetic field. And then finally, the temporal part of the this electromagnetic field here, A0, this is satisfies an elliptic equation here. So this is somehow enslaved by the dynamical variables, which are phi and the AJs. Now it turns out that the nonlinearities occurring in the equations for the AJs, they have a very, very nice structure. There are derivatives which are occurring here. There is an inverse derivative which occurs on the outside. And the fact that there is this inverse derivative on the outside, it means that actually this paraproduct problem, which comes up, which I've discussed before, it does not come up for the equation in the AJs. So the AJs are somehow the nice variables. There you don't have any issues. The only difficulty here is really residing in the equation for phi. And if you write down the equation for phi, you will find a magnetic interaction term between the potential A and the derivative of phi. And there the paraproduct issue again comes up, which causes difficulties. Now, so this system, it has a conserved energy. It comes with a natural scaling transformation. And then, of course, you have the usual rigmarole that you have the energy critical case where the critical Sobolev space is exactly equal to the energy. This is the case when D equals 4. When D is less than or equal to 3, then the problem is subcritical. And when it's larger than 4, then it's supercritical. And a lot of works have been done related to this problem. So roughly speaking, if you are at least epsilon above the SC, the scaling critical regularity, then you're strongly locally well-posed. This actually holds true all the way up to dimension 3. And you can then ask, well, what about global well-posedness? So again, in the D equals 4 case, the SC critical Sobolev exponent equals 1. And in this case, very recently, a very complete theory has been established. In the case when D equals 3 or 2 or 1, this is sort of classical. There's work early in Moncrief in the 80s, which already showed that NKG has global solutions for large, nice enough data. And then in the 90s, Klainerman-Tataru, they revisited the D equals 3 case. They showed that we actually have well-posedness in H1 in the Coulomb gauge, which is above H1 half plus epsilon, but it was already much of an improvement. And then in 99, Klainerman-Tataru, they basically showed HSC plus epsilon well-posedness in the energy critical case. And in D equals, then in 04, there was a further improvement when Macedon disturbance, they went back to the D equals 3 case and improved the Klainerman-Tataru result by showing that you indeed have H1 half plus epsilon. So you just 1 epsilon above the scaling critical regularity is enough in the Coulomb gauge, as usual. And so again, finally, in the energy critical case, in 2015, it was shown that for arbitrarily large initial data, provided that they're smooth enough, such that you have a good local theory, actually solutions exist globally and the problem is globally well posed. All right, so this is all kind of a very quick summary, omitting lots of things, but I mean, I can't cover everything here. But the basic question that I want to answer now is, of course, all of these results, you have regularity at least equal or more than the scaling critical Sobolev regularity. And the question now is, can one go below this regularity? So in particular, in the energy critical 4D Maxwell-Klein-Gordon system, is it possible to construct, let's say, global solutions whose regularity is strictly less than that of the energy? And again, like I said, so the main difficulty comes from this the equation for the particle field, which has this magnetic interaction term, AJ times del J phi. And again, the paraproduct issue comes up. And this paraproduct issue, it destroys, again, the basic Bourgain, the Paraproducts ansatz. Now, still, nonetheless, one can do something here. So now let me state the result, which is kind of the main content of this talk. So let's now fix the D equal 4 situation, the energy critical case for the Maxwell-Klein-Gordon system in the Coulomb gauge. Let us look at data for the electromagnetic field, which is a pair of vector fields A and B. And also specify data for the phi field, the particle field. And then let us randomize these. So one has to be a little bit careful. So that's why I've written this down very carefully. Maybe it looks a little confusing, but I mean, it is really the same thing that we had done before. It's the Wiener randomization. You just have to make sure that the randomized electromagnetic fields data are still real valued. And I mean, such a constraint is not present for the particle field. But anyway, so you randomize your initial data in the Wiener way. This randomization is not going to destroy the Coulomb gauge property, so that's very important. And so last year, together with Jonas Biermann and Gigliola Staffilani, so we managed to show that with these kind of randomized data, we can show global existence for this model for data which are strictly below H1. So the theorem says the following. So there is some very small delta star, which tells you how much you can go below the critical H1 regularity for your data. And there is an epsilon, which tells you how small your data have to be, such that with the exception of an event which is very unlikely, so it's decaying very rapidly, super exponentially in terms of the inverse square of the size of your data, you can construct solutions for your randomized initial data. And these solutions are global in time, and they decouple into a, again, formally similar to the Burg-Tzvetkov result, into a rough part and a more regular part. Okay. There is also a certain uniqueness for these solutions, but that's a little complicated to describe. It will emerge from my discussion of the result later on. Okay. So it appears that this is the first such global existence result for data below the critical regularity for one of these geometric wave equations, which involve this sort of severe paraproduct issue. And we believe that a similar result can be proved for many of the other such geometric wave equations by using a similar approach. Okay. Now, so again, I kept mentioning this paraproduct issue. So let me talk a little more about this. Let me tell you, I mean, we were not the first ones, of course, to encounter this. This has come up again and again. And sometimes it comes up in a way which is somewhat more mild, and sometimes it comes up in a way which is more severe. So for this result, which I just mentioned, it's very severe, this paraproduct issue, but in other situations, it was more mild. And very influential for us for this result was a paper by Wozniacki and Tao from 2004, where they introduced certain very important technical tools. So in this paper, they looked at the Maxwell-Klein-Gordon equation in the Coulomb gauge in very high spatial dimensions. And the question that they asked there was not random data. I mean, they wanted to construct smooth solutions, but they wanted to have an optimal condition in terms of the initial data. Like, you know, what kind of smallness do you have to require for the initial data to be able to construct a global smooth solution? And it turns out that, so kind of optimally, again, what you expect is that the critical Sobolev norm has to be small of your initial data. And for wave maps, if you want to prove such a result, basically you can do this by implementing a smart gauge change, and you can sort of get rid of this problematic paraproduct term. But for this equation, the Maxwell-Klein-Gordon equation, this does not work. But somehow the difficulty that the paraproduct poses is really kind of mild, in the sense that if your data is just a little bit stronger, so instead of assuming smallness in h.sc, you assume smallness in b1.sc. So instead of square summing over the different dyadic frequencies, you L1 sum over the frequencies, then this paraproduct issue goes away, and you can move the paraproduct as a source term to the right-hand side. So it's really very, very mild. But it's very important because it led them to introduce certain very important tools. Now, okay, so one can even say more. So like I said, for the equation for this A potential, this equation is better. It has a better structure. And so one can decompose A into the free evolution of its data and a nonlinear part. And the nonlinear part, even if your data are only small in h.sc, the nonlinear term immediately inherits this better summability property, this b.1 sc property. So somehow the contribution of the nonlinear part to this paraproduct term is already negligible, and you can just insert the free part of A into this paraproduct. That's your real enemy. And so then, but there you can't simplify things anymore. And so you wind up with this magnetic potential wave equation here. And Wozniacki-Tao realized that they could actually solve this equation by means of some kind of very interesting approximate parametrics, which allowed them to recover basically most of the estimates that you have for the normal wave equations, Strichartz estimates, XSB, and so on. All of these complicated estimates can be recovered by means of approximate parametrics for this kind of thing. I will talk more about this if I have time later on. A more severe incarnation of this paraproduct issue, this was in this large data result due to Luhrmann and myself to the large data problem for the energy critical Maxwell-Klein-Gordon equation, and similar to the large data problem for critical wave maps, which I addressed with Wilhelm Schlag in 2009. So our approach to this problem is by means of the concentration compactness method and profile decompositions. And specifically, so what one is led to do is one is led to consider sequences of solutions to this problem, which are large, but of bounded energy. And what one wants to do is one wants to implement a kind of profile decomposition for these solutions in the style of Bahouri-Gérard, who did this for the energy critical nonlinear wave equation box U is U to the 5, let's say, in 3 dimensions. And if you want to do that, then you run into this paraproduct issue. You get interaction terms between constituents, between pieces of A and phi, which are at very different frequencies. And you cannot show that these interaction terms asymptotically vanish as n goes to infinity. And so this means that one of the key ingredients of this Bahouri-Gérard concentration compactness method fails here. So how does one address this issue? Well, it's sort of similar to what Björn Brinkmann is doing in his setting, which was later than this. So one builds these problematic interaction terms into the wave operators which define the concentration profiles. Okay, so that's what we call this covariant procedure. But of course, in order to implement something like this means you break the symmetry between low frequencies and high frequencies. You can extract the profiles for the high frequencies, provided that you already control the low frequency part of your solution. So this means you need some sort of induction on frequencies to construct your solution, starting from low frequencies and then going to higher and higher frequencies. And in this setting, this is somewhat complicated because, of course, this depends on where the energy concentrates. So this is very much dependent on the sequence of solutions A and phi. All right. Another severe incarnation, again, is for this result that I want to discuss now, this work with Luhrmann, Staffilani, and myself. Again, there is this interaction term, low frequency in A times high frequency in phi. And this term does not gain any regularity, even if you apply the Duhamel parametrics to it, even for randomized data. So how do we deal with it? Well, in some sense, what we do is very similar to what Brinkmann does. So we take part of this problematic paraproduct interaction term, strongly imbalanced paraproduct, where you reduce the frequency of the low frequency part in A to size n to the gamma, for some gamma which is strictly less than 1, so that there is a definite frequency separation between these two pieces. And you build that into your wave operator, and the rest, an error, you move into the right-hand side. And then the idea is that you sort of construct your solution inductively. For each frequency n piece, you solve this kind of equation here, assuming that you already have some kind of good control over the parts of the solution which are at low frequency. Okay, so how do we solve this strongly imbalanced paraproduct wave equation here? Well, by means of approximate parametrics in the spirit of Rodniansky and Tao. But there are some important differences here, but probably I won't have the time to discuss this. And then the idea is that one shows redeeming estimates, so bounds which beat the scaling for solutions of this kind of wave equation here. The important point again being that whatever randomization you implement for the initial data survives to some extent for the solution of this magnetic wave equation here, although the frequency support gets smeared out. So the randomness gets kind of smeared out, but some of it survives so that you still prove some redeeming Strichartz type estimates and so on. And on the other hand, on the right-hand side, everything that's on the right-hand side that's left has the smoothing property once you apply the parametrics now corresponding to this wave equation on the left, of course, so that you again implement some version of the Bourgain-D'Aprato-Debuche decomposition. Now, maybe I should talk a little bit about how this induction procedure really works. So it may be a little abstract. So basically the idea is that you obtain the solution corresponding to your randomized rough data as the limit of a sequence of solutions corresponding to truncated data. And of course, there has to be some starting point. Okay, so we will show that this sequence of solutions that you obtain then will almost surely, or with high probability, converge to something which has the desired structure and has all this desired bounds. To start, of course, you have to start somewhere. So you set n equals 0, you just look at the part of your initial data of frequency less than or equal than 1, say. And of course, this part is C infinity, so there's no problem. You can evolve it globally even without randomizing by simply involving the classical theory for this problem, let's say. And then there's an induction step. So assuming that you have controlled the evolution of your data truncated to size n-1, you have then to pass to the next truncation. And this means you have to control these increments, which are denoted axn and phi n here. And well, I mean, so how do we do this? Well, I mean, like you derive equations for axn and phi n, which will involve the low frequency parts. And so to have any chance of getting kind of good estimates on these phi n and axn pieces, you have to make some assumptions that the low frequency parts are actually bounded in some sense. And we will show that this is with high probability is the case, but of course there are infinitely many such steps. So you have to make infinitely many such assumptions. And in order to organize this a bit, so we use a method that was introduced by de Bois and de Buch. We introduced these cutoffs, chi sub epsilon less than n-1 here. These cutoffs simply include all the information that we want on the low frequency pieces, certain improved Strichartz norms and so on and so forth. I won't go into details. And this cutoff is 0 unless these bounds are all nicely behaved. So unless all the pieces, the low frequency pieces satisfy good bounds, are of size at most epsilon. And then, okay, then we have to control these increments, axn and phi n. Like I said, the equation for the A part is much better behaved. So you get a Burg-Tzvetkov splitting there by simply writing axn as the free evolution of the frequency n part of the data plus a nonlinear part, which gains regularity. But for the phi field, this is much, much more difficult, all right? It turns out you get a similar splitting. You get a splitting into a rough part and a smooth part. But the definition of the rough part and the smooth part is very different than the original Burg-Tzvetkov method. Because to define this phi and air part, the rough part, one has to use solutions of this modified wave equation involving the strongly imbalanced paraproduct here in terms of the this magnetic potential interaction term. And all right, so then for the next step, so you multiply this phi and r with this cutoff so that you ensure everything's well defined. And then the key kind of to make sure that this whole this inductive procedure converges is essentially contained in this following proposition and similar propositions for the other components. So one shows that to large probability, these truncated increments are bounded, they satisfy good redeeming bounds that beat the scaling in terms of a supercritical norm of the initial data, and similar for the other components. And then you do that for each n, right? And of course, to show that at the end everything makes sense, that you get a solution of your equation, you have to show that there is an event of large, essentially likelihood equal to 1, such that all of these cutoffs are actually equal to 1, and such that all of these bounds are non-trivial, if you want, so that none of these phi r n chi are set equal to 0. So that's kind of the outline for the inductive procedure. Now, yeah, I don't know if I started a little late, so I don't know if I still have a little bit of time.
Maybe a couple of minutes. If you
Right. So this is the master outline. So now what are, as you see, like basically one combines various ingredients. One combines this induction on frequencies philosophy, which played an important role in this concentration compactness approach to the large data classical solutions for Maxwell-Klein-Gordon in the critical case and so on. And there's this parametrics construction that's due to Rodniansky tau, And so let me talk a little bit about this parametrics construction, which is actually quite interesting. And there are some interesting new difficulties that occur in this setting. So how does it work in the Wozniacki-Tau setting? Remember, like this was the mild incarnation of the paraproduct issue, where one tries to show global existence of classical solutions where the initial data are small in the HSC norm, and one works in high spatial dimensions. And they're trying to solve this magnetic potential wave equation. And basically the idea is that instead of working with the this usual Fourier parametrics for the that solves the free wave equation, one introduces a modification. One introduces an extra twist function here. Now, so there's this psi plus minus term here. And one is trying to choose this in such a way that one gets maybe not an exact solution, but at least one gets a solution which is good enough, such that whatever error is made is somehow smaller or better in some sense. And now if one writes down the equation for this psi plus minus, then it turns out, okay, I mean, there are of course many terms. There are certain terms that are quadratic in psi, and then there are terms that are linear in psi. And the leading term, the leading order term that arises is when one derivative falls on psi and the other derivative falls on this the e to the plus minus it psi plus x dot psi exponential. And then you get some sort of transport equation for this phase function psi. And okay, one of course can try to solve this as a transport equation, but it turns out then one doesn't get good bounds for this. So instead, what Wozniacki and Tau do is they exploit the fact that in their mild incarnation of the paraproduct issue, they can assume that this electromagnetic field potential is actually a solution of the free wave equation. And then they can write down a very nice explicit formula in terms of an elliptic operator, maybe something surprising. This exploits the fact that A is a solution of the free wave equation. So you get this, it's almost like a Laplace inverse operator that comes up here, but it's actually a very degenerate Laplace inverse. So there's like a higher degeneracy than for the usual Laplacian. And now this expression is too singular. And so in order to actually make sense of this and get good bounds, they have to truncate things a little bit. They have to excise part of this AX free potential, and the corresponding error, they move into the source because you gain something there. And then for the non-excised part, for whatever's left, you can prove that you get good bounds. But this very much hinges on the fact that this AX free is a solution of the free wave equation here. Now, okay, there are other features that are very special in this setting. For example, all the errors that they're generating by means of their methods, with the exception of the part that's due to excising, to cutting out a little bit out of this AX free, all the other errors are actually quadratic. They're like nonlinear in AX free, and so you gain a lot that way. Now in our setting, it's much worse. You cannot just build in the free part of the evolution of AX. You have to build in the full AX, the low frequency part of AX. And this leads to lots of difficulties inverting these, solving this transport equation. Also, one cannot avoid generating error terms which do not gain any regularity here. So this is again a problem with like the Bourgain-Daprato-de-Bush trick. And so in particular, to deal with this last issue, you have to sort of do an infinite reiteration of this parametrics due to Wozniacki-Tau. So in other words, to actually obtain the rough part of your phi field, you have to write it as a sum of infinitely many pieces. And each one of these pieces arises by applying this approximate parametrics due to Wozniacki-Tau, or more precisely a modification of it, to whatever rough part you generated before. And of course, this is dangerous because at the end you want redeeming bounds for this rough piece. And of course, every time you apply these parametrics, you smear things out. So you have to make sure that in the end you don't smear things too much so that you lose all the randomness. But all of this can be done, right? And on the other hand, of course, like whatever delta star you generate to go below H1 regularity is very small. So it's like 100th or something. So how much you can push this method, like how rough the initial data can be to actually get such a result, I don't know at all. But it might be interesting to sort of get a sense like what one might be able to expect here. So it's all built on a very delicate balancing act to balance on the one hand, preserving randomness, for your parametrics part and obtaining smoothness for whatever is left, smoothness gains for whatever is left. Now, there are a lot of further projects you can do. Of course, this is the simplest incarnation of these geometric wave equations. You can also look at the situation when you have a non-abelian gauge group, such as the wave maps with general targets or the Young-Mills equation. Or you could even look at fully quasi-linear equations and try if one can repeat some of these things. One can also look at the situation, what happens for large data. Of course, this is a small data result that I talked about. Can we evolve large data of regularity much less than H1 and still affirm that this leads to global solutions? And a last aspect I'd like to mention is, again, like I think like the randomization still offers lots of opportunities, even in the context of classical solutions, where sometimes there are certain obstacles to classical, to constructing classical solutions, which may be circumvented by using this randomization method. And for example, maybe showing that you can get much better bounds on scattering norms than you would actually expect generically. So I think there's a lot of potential in this. And so let me just close with this.